Why is a black body the perfect absorber and emitter of radiation? Imagine a surface that absorbs every bit of light or electromagnetic wave that hits it, no matter the wavelength or direction. It sounds like a science fiction idea, but in physics, this is what a black body does. A black body is considered the ideal object in radiation, heat transfer, and designed because it absorbs all incident radiation without reflecting or transmitting any. This total absorption means it acts as a perfect sponge for electromagnetic energy. When it comes to emission, a black body radiates energy at the maximum possible rate for its temperature. This is because, according to Kirchhoff's law of thermal radiation, an object that absorbs all radiation at a given wavelength must also emit the maximum radiation at that wavelength when in thermal equilibrium. In real life, no perfect black body exists, but we can closely mimic one using a cavity with a tiny hole. Radiation enters the cavity through this small opening and bounces around inside, hitting the walls repeatedly. Because the walls are usually made of highly absorptive material, almost all the radiation gets absorbed. The radiation that escapes from the hole then represents blackbody radiation, which depends only on the temperature of the cavity and not on the material itself. This makes blackbody radiation a standard for understanding how objects emit energy. The spectral distribution of this radiation follows Planck's law, which tells us how much energy is emitted at each wavelength for a given temperature. As the temperature increases, the total energy emitted rises dramatically, following the Stefan-Boltzmann law, which states that the energy radiated per unit area is proportional to the fourth power of the temperature. Additionally, Wien's displacement law explains that as temperature goes up, the peak wavelength shifts toward shorter wavelengths, meaning hotter objects glow with bluer light. The core reason why a black body is both a perfect absorber and emitter comes from Kirchhoff's law. It states that at thermal equilibrium, the ability of a body to emit radiation at a certain wavelength equals its ability to absorb radiation at that wavelength. Since a black body absorbs all radiation, its absorptivity is 1, which makes its emissivity also 1. This perfect balance makes it the benchmark for understanding radiative heat transfer. In mechanical engineering, knowing how black bodies behave helps us design systems involving radiation, like furnaces, radiative heaters, and thermal insulation. Engineers often compare real surfaces to black bodies by using the concept of emissivity, which measures how close a surface is to being a perfect emitter. Most real objects are gray bodies, with emissivities less than 1, but the black body remains the ideal model for calculations and comparisons. To sum up, a black body is the perfect absorber because it takes in all incident radiation without reflection or transmission. It is the perfect emitter because it radiates energy at the highest possible rate dictated by its temperature. These principles are fundamental in understanding how heat transfer through radiation works and are essential tools in designing efficient thermal systems.